In the lecture on ancient astronomy, we talked about the geocentric model and how until about 1500 AD, the common accepted view was that the Earth was at the center of the solar system and that all the planets and also the Sun all orbited around the Earth. We now know that's not the case. We now know that the Sun is actually at the center of our solar system, what we call the heliocentric model. But what led to that change? Well, part of what led to that change was the fact we started making better and better observations of where the planets were located. What you see here in this picture was roughly Ptolemy's idea of how the solar system worked about 100 AD. You had the Earth in the middle. You had Mars's orbit around the Earth, but Mars was sitting on one of these epicycles. And as Mars went around the epicycle, the whole epicycle went around the Earth. Thing was, as they made better observations, they realized, you know what, Mars is not exactly where Ptolemy's model says it should be. Well, astronomers said, oh, hey, no problem. No problem. We know how to fix that. We can just add another epicycle. So they said, oh, wait, well, really what's happening is Mars is sitting on this epicycle, and it goes around this epicycle, which goes around this epicycle, which goes around the Earth. And now we can match our observations. And that worked until we made better observations. Again, realized, oh no, it doesn't quite match up. How can we fix that? No problem, add another epicycle. And by about 1500 AD, in order to explain the orbits of the 5 planets that were known, we needed literally 40 to 45 epicycles. So on average, each planet had about 8 or 9 epicycles. It looks something like this. So great, we have no problem explaining the universe, explaining the solar system. Mars is sitting on this epicycle, and it goes around it, which goes around that, which goes around that, which goes around that, blah, 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 and so on until you get back to this one going around the Earth. It was a total mess. It was around 1500 AD that someone started asking, could there be a better solution? And that better solution was what's called the heliocentric model. Helio means sun, so the sun at the center. That person who was asking, could there be a better solution, was the person you see right here, Nicholas Copernicus. His idea was we put the sun at the center and planets orbit the sun in circles, and that included the Earth. The Earth was a planet after all. The Earth orbited the sun in a circle as well. Let's see how the heliocentric model just made a lot more sense than the geocentric model. We're going to do this by looking at this website you see right here. Here we have a setup of the heliocentric model. We've got the sun at the center. We've got the Earth here. Here we have, we'll say, Mars. Let's put this animation in motion. I'm going to speed it up a little bit. At the bottom, you'll see the motion of the sun through the celestial sphere. You'll also see the motion of that planet through the celestial sphere, where the planet appears to be in the sky. Watch for a while, and you'll see every so often the planet seems to move backwards. There it goes, backwards a little bit. Backwards a little bit. You get that retrograde motion. So the retrograde motion is happening as we would expect in the sky. But see if you can notice in the orbits up here what's actually happening when you get retrograde motion. I'll slow it down just a little bit. Here we go, retrograde motion. Wait a little bit more, retrograde motion again. What's happening to cause that backwards motion, that appearance of backwards motion, is just the Earth, here we go, is passing by the other planet. Coming up right again right now, there you go. So when the Earth passes by a planet, it makes it look like that planet is going backwards compared to the background stars. You might experience this in your everyday life. Maybe you're driving on the freeway, and as maybe you're going 61 miles an hour, and you pass a car that's going 60. as you sort of pass the car, it looks like that car is going backwards for a moment. Even though really it's not. It's going forward at 60 miles an hour. Because you're passing it by, it looks like it's going backwards for an instant. Same thing happening here. The planet is not actually going backwards. It just looks like it's going backwards from the perspective of the Earth. Okay, what about a planet like Mercury and Venus? Mercury and Venus are closer to the Sun than we are. So how do they get retrograde motion then? I'll stop the animation. Let's set this up. We can move the other planet closer now. So now we've got Earth on the outside. Here's, say, Venus. Here's the Sun. Let's put the sky in motion again. You'll see that there goes the planet, and there's retrograde motion. Keeps going around, normal motion, and retrograde motion. So it's not actually just the Earth passing by another planet. It's also when another planet passes by the Earth. When Venus, coming up right here, passes by the Earth, you get retrograde motion. So retrograde motion happens whenever a faster planet passes by a slower planet. And from Earth, it doesn't matter whether we're the planet passing by another planet, like when we pass by Mars, or when another planet passes by us, like Venus. The planet still appears to go through that backwards motion. You'll also notice another nice thing about the heliocentric model. It explained a really interesting thing. When you look up in the sky, you always see Mercury and Venus in the sky near the Sun. You'll never see Mercury and Venus in the sky at midnight. All the other planets you do see at midnight, just not Mercury or Venus. That was hard to explain in the geocentric model. But in the heliocentric model, it actually made quite a bit of sense. If you look at the diagram here, if you're looking, I'll actually pause it, make it a bit easier if I pause it for a second. Here we are on the Earth. Here's the orbit of Venus. No matter where Venus might be in its orbit, it's always roughly in the same direction as the Sun. You will never have Venus over here in what we call opposition, the opposite side of the Earth from the Sun. Mercury and Venus, because they're closer to the Sun than we are, will always be located roughly in the direction of the Sun. So back now to our slide on the heliocentric model, and you'll see two of the sort of important takeaways from this model. One, retrograde motion is just explained when a faster planet passes by a slower planet. You don't need any of those fancy epicycles or things like that happening. Also, it's much easier to explain why Mercury and Venus are always seen near the Sun and never at midnight. Much easier to explain in the heliocentric model than the geocentric model. What you had really with the heliocentric model is a great example of Occam's razor. The idea of Occam's razor is if you're presented with two choices, the simpler solution, two solutions maybe, better way to put it, two solutions, the simpler solution is normally the one that's right. Here we had an example where to explain the orbits of the planets around the orbits of the planets as we saw them in the sky, we could either say the Sun is at the middle, or we could say the Earth is at the middle, and we have all these epicycles. This is an ugly mess. This a lot simpler. Good example of Occam's razor. But the interesting thing about this is it still was extremely controversial when Copernicus came up with this idea of the heliocentric model. People were very, very, very unwilling to move away from the idea of the Earth being at the middle. There are a few reasons for this. One, it just doesn't quite match what we experience. I don't feel like I'm flying through space right now as I go around the Sun. You don't feel like you're flying through space, but we are. Because our motion is fairly constant, we are not feeling that change. But the reality is we are flying through space. But 1500 AD, people were like, well, I don't feel like I'm moving, so how could we be flying through space? Also, there was quite a bit of egotism involved. It feels nice to think, hey, we're at the middle, we're at the center, it's all about us. And there was also quite a bit of pressure from the Catholic Church at the time, which had adopted this view that the geocentric model was correct. The Earth was at the middle. In fact, Copernicus wrote this very important book about the heliocentric model, but he told his friend, I've written this book, it's extremely controversial. I don't want to get in trouble with the church, so don't publish this book until I'm dead. He was that afraid of what would happen to him because of these extremely controversial ideas. He was probably right to be concerned. We'll learn about Galileo in a lecture coming up, and he got into a ton of trouble 100 years after Copernicus for essentially the same idea, for supporting the heliocentric model. Funny sort of side story, Copernicus's friend did listen to him, and when Copernicus had died, he published Copernicus's book. But he was even concerned about how Copernicus's legacy, or how his soul might be treated by the church, that he actually added a little forward to the book at the very beginning, saying, here's this book my friend Copernicus wrote. But he was just having fun. He didn't really believe this whole sun being at the center thing. He was just trying to protect his friend. Now, in fairness, Copernicus was not actually the first person to come up with the heliocentric model. This guy here on the right, Aristarchus, was actually the first. And you'll see he lived a long time before, almost 1800 years before Copernicus. Copernicus did not know about Aristarchus, so he came up with his idea of the heliocentric model on his own. We only found out about Aristarchus's writings about 100 to 200 years ago. Why was Aristarchus's ideas completely ignored more than 2,000 years ago? Well, it's pretty easy to explain, actually. How many of you have ever heard of Aristarchus before this lecture? I'm guessing not many of you. How many of you have heard of Aristotle? Probably a little bit more. How about Plato? Socrates? These are sort of those names that we've all heard about, the big names from ancient Greece. All of those big names were all supporters of the geocentric model, the Earth being at the middle. So here we had Aristarchus, little guy with this crazy idea. Oh, the Earth's not in the middle, the sun's in the middle. And the popular philosophers at the time, Plato, Aristotle, Socrates, they were all like, oh, ignore him. He's that weirdo who thinks the sun's in the middle. And his idea got completely pushed aside. But now he does get the last laugh because he was right. He was right. Copernicus was right. The sun is actually at the center of the solar system. The Earth and all the planets orbit around the sun. We're going to find out, though, in the next lecture that Copernicus didn't exactly get it right. He was very close. He was right about the sun being in the middle. But he still didn't quite get his model right. What's the correct model? For that, we'll have to turn to a very important figure in astronomy, Johannes Kepler.